Kristen Atchison here, and we're still talking about ANOVA. Now we're going to focus on post hoc tests, which is something that we do after our hypothesis testing. So post hoc tests are a kind of pairwise comparison. And we do these because ANOVA is an omnibus test. If you're not familiar with omnibus means, it means that it's comprising several items. So think back to our null hypothesis and our research hypothesis that we do in hypothesis testing for ANOVA. So our null hypothesis is that everything's equal, right? mu1 is equal to mu2 is equal to mu3. That there's no difference anywhere, right? That's our null hypothesis. And our research hypothesis, when we write that out mathematically, we write out is not the null. And the reason we do that is because there's a whole bunch of different ways that there could be differences. None of the populations could be equal to each other. Two of the populations could not be equal to each other, but which two? When we reject the null hypothesis, we're saying that the population means are not all the same. But we don't know where that difference is. Somewhere, our ANOVA, our omnibus ANOVA, tells us that somewhere between all those means there is a difference, but it doesn't tell us specifically where. And that's where post hoc tests come in. ANOVA compares all the mean differences simultaneously in one test, and that's why it's an omnibus test. So this significant F really just indicates that there's at least one difference somewhere in all of that is statistically significant. It does not indicate which means differ significantly from each other. So even if you look at the data and you're like, okay, well, I think the difference is here, that's what post hoc tests are for. Post hoc tests will say, yeah, that is where the difference is. That will give you that statistical confirmation that this is where it is. So post hoc tests are these follow-up tests that are done to determine exactly which mean differences are significant and which are not. And they're called post hoc tests. Post meaning we're doing them afterwards, right? Okay? So this is something that we're doing after hypothesis testing when we find that significant F. And we use these post hoc tests, which again are a kind of pairwise comparison, to tell us if two populations are different from each other. We can follow up. If we do this ahead of time, we can plan to do this ahead of time, and then they're called planned comparisons or a priori comparisons or contrasts. So then they're not called post hocs, they're called something different. So if we decide ahead of time before we do our statistics, okay, well, I want to do an ANOVA because I want to see, is there a difference somewhere in all of this? But I'm really interested in looking at this difference between these two levels. If you made that decision ahead of time, that's called an a priori comparison. And we're not going to calculate those, but it's the very similar idea. It's the very similar process. The difference is with post hoc tests are these follow-up, right? We're going to go say, okay, well, I conducted the F, I found something, and now I'm really interested in the difference between level 1 and level 2. And so we go back and we make those comparisons. The problem with these post hoc tests is alpha adds up, right? So post hoc tests compared two different individual means at one time in this pairwise comparison. And each time we do a comparison, each time we do a statistical test, we get a chance of type 1 error, right? And typically we set that as 5%. We say, okay, I'm willing to take a 5% chance risk of committing a type 1 error. But when we do several comparisons, when we do an ANOVA and then we do something else and something else, all of those things add together and it accumulates and our risk goes up. This is called Experimentwise Alpha. It's the accumulation of all of these comparisons, of all of this risk of a type 1 error, and it increases the probability that we're going to make a type 1 error. Again, us as researchers have decided, no, we're not very comfortable with saying there's an effect if there's not an effect. So we set that low and we want to keep that low. And so we have limited number of kinds of comparisons that we can do. So we can't go back and do a t-test after we've done this ANOVA to see if there's a difference, because that's going to make our Experimentwise Alpha go way up. Okay, that's why we're not going to just go back and do a t-test. That's why we have something else. These post hoc tests or these post tests are special methods that have been created to try and control that experiment-wise type 1 error, trying to limit how much risk we're willing to take. Okay, and so there's two different ones that we're going to talk about in this class. There's a bunch of different kinds depending on the kinds of statistical methods that you're using, depending on what you're interested in, but these are the two we're going to talk about in class. The first one is Tukey's honestly significant difference. Notice that says Tukey. There's not an R. It's not turkey. This is not Thanksgiving. So Tukey's honestly significant difference. And this is really a single value that determines the minimum difference between two treatment means that's necessary to claim that there's a difference. And again, this is going to be limiting some of that experiment-wise alpha, which is what we want. This is the formula for Tukey's HSD. Q is a value you get from a chart. Because we're trying to limit this, it's got its own statistical table so that we're really minimizing that risk of that experiment-wise alpha. So we'll go look that value up. You do have access to that chart on iCollege, but for this process, for this discussion, I'll give it to you, okay? So, an important note, you can only use Tukey when groups have equal sample sizes. Write this down. It's not in the lecture outline. It got added afterwards. You can only use Tukey when the groups have equal sample sizes. So if group 1 has 10 people, group 2 has 10 people, and group 3 has 9 people, nope, cannot use Tukey. This can only be used with equal sample sizes. The other one we're going to look at is the Scheffé Test. The Scheffé Test is one of the safest possible post hoc tests, okay? And what we mean by safe is that it has we've limited experiment-wise alpha the most, okay? We have limited that risk. That's what's safe about it. We've limited that risk of committing a type 1 error. So this is one of our safest tests here, the Scheffé Test. And it uses an F ratio similar to the way that we do in the traditional ANOVA to evaluate a significance of differences between two treatment groups. And this is the formula that we use. And what we're going to do is we'll recalculate mean squared between using just the two groups that we're interested in. Mean squared within will stay the same, and we do that because it is more conservative that way. So here's that criminal record study that we've already done. That was a previous example. And so we're going to go in and do both a Tukey test and a Scheffé test using this previously calculated data, this previously calculated information. So go back and find your notes on that. Go back, look at the video if you need to. I just didn't want a super long video, so this is why we're doing two separate ones. Okay, so first we're going to do Tukey's HSD. That mean squared within that we calculated for the criminal record example was 5.33. We had an N of 5 in each group. Now this is why you can only use Tukey when you have equal group size. If your groups are equal, if you have 5 people in one group, 6 people in another group, and 4 people in another group, which N do you use, right? That's why you can only do it when the sample size is equal, because it's not asking you for big N, it's asking you for little n. It's asking you for how many people are in each group, and that's why you can only do this when they're the same, okay? What you'll use to look up that Q value in the chart is you'll use K and degrees of freedom within. So previously we calculated K at 3, that's the number of groups that we had, and our degrees of freedom within was 12. Using the table, we look those values up and we get a Q of 3.77. So now we'll do the math, right? So we take 5.33 divided by 5, take the square root of that, multiply it by 3.77, and we get 3.89. Okay? So again, what we did here is we took 5.33 divided by 5, took that value, took the square root of it, multiplied it by 3.77 to get 3.89. And again, this is a single value that determines the minimum difference between a treatment means that's necessary to claim that there's a difference there, okay, this HSD. So we're saying that anything bigger than 3.89 is a statistically significant difference between two groups. One of the reasons this isn't as safe as Scheffé is we're going to take this one number and we can look exactly where the differences are. We can look in all the groups. We don't have to just pick one pair to look at. We can look at all of the pairs. And so this is why it's going to have more Experimentwise Alpha than Scheffé will, but it still is limiting it compared to doing, say, t-tests or another ANOVA or something like that. Okay, so the difference between criminal group 1 and criminal group 2 is 4. The difference between criminal group 2 and group 3 is 1. And the difference between group 1 and group 3 is 3, okay? So remember our HSD was 3.89, so anything bigger than 3.89 is a statistically significant difference. Again, we're finding that this first group here, this first comparison, group 1 versus group 2, it meets that criterion. It meets that 3.89. It's greater than 3.89. So we can say in our omnibus test, where we got a significant F, this difference here, the difference between the criminal record and the clean record, is what's driving that effect. We now know where that difference is coming from because of this post hoc test, this Tukey test. Okay, so now we're going to do the Scheffé. Again, Scheffé is super safe. In that last example, we got to look at all 3 of the pairs, right? We're not going to be able to do that here. Here, we're going to have to go in ahead of time and say, okay, which 2 do we think are driving the effect? Now, that was pretty easy. If you look back, right, we have 3 different groups. Which one's the biggest, right? Well, the biggest difference is between group 1 and group 2. So that's where we're going to go and we're going to look for the Scheffé test as well, okay? So again, we're only going to look at 2 groups. We're going to need to recalculate the mean squared between for those 2 groups that we're interested in, okay? And then we'll again use the mean squared within that we already had because, again, that's the estimate of the variance, right? We're estimating the variance of the population. We're estimating how much variance there is in the population as a whole. And if we do that with all 3 groups, it's a better estimate than if we do it with just the 2 groups. So group 1, group 2, these were our T values. We got 40 for the criminal group. We got 20 for the clean record group. We got a G value of 60 then. So we'll add those 2 values together to get our G. I also have on here the x squared, the sum of x squared. If you really wanted to go about it, the total direction, the sum of squared total direction, but there's really not a point. So we'll use that G value of 60, that T value of 40, and that T value of 20. So I've transferred that over here. We're going to have a new N, a new big N, because we're only looking at 2 groups now. We're not looking at 3 groups. We're not looking at all 3 of them. So we're not looking at a big N of 15. We're looking at a big N of 10, because we've only have 10 scores in that G value. That's what it's asking you. That's saying, okay, how many scores went into that G? Well, 10 scores went into that G, and so that's the value that we're going to use. So what we'll do, what we'll do is we will take T squared 40 divided by little n, which will be 5. We'll add that value together with 20 squared divided by 5, add that value together. We sum those values just like we have previously. And then we'll subtract it from 60 squared divided by n. Okay, so now we're going to go in and do our degrees of freedom. We're still going to use that same degrees of freedom between, okay? So degrees of freedom between, when our original calculation was based on the fact that we had 3 groups. So 3 groups minus 1. Well, we're only looking at 2 groups here, right? This is one of the reasons why it's so safe. We're hedging our bets, okay? We're saying, yeah, we're only looking at the variance between 2 groups, but we're going to go ahead and divide it by a bigger number. So we're minimizing that risk. We're saying we're making it even harder for there to be a significant difference, okay? So again, our degrees of freedom between will be our original degrees of freedom between. That's 2. And again, that's one of the reasons it's so safe is because it's allowing us to kind of hedge our bets and reduce that risk. So the sums of squared between that, our new sums of squared between that we calculated previously was 40. Our old degrees of freedom between that we used before was 2. So we take 40 and we divide it by 2 and we get 20. So our mean squared between is going to be 20. That's what we have here. We're going to use our mean squared between. We're going to use our previously calculated mean squared within. So 20 divided by 5.33 is equal to 3.75. Our cutoff using our our F table was 3.89. So this is the second reason that this is so safe. We're using the same stricter criterion as the omnibus test. So again, we're making it harder to find a significant effect, which means we're reducing our risk of a type 1 error. That is why the Scheffé test is so safe compared to other post hoc tests, and especially compared to other analyses. So again, the Scheffé is one of the safest of all possible tests, and again, it's using this similar F ratio where we do hedge our bets, where we do use stricter criterion to find that significant difference. Notice here, our 3.75, our cutoff is 3.89, so we don't find a significant difference between these two groups. Notice that here. We did find a significant difference using the Tukey test, right? In our Tukey test, we said, oh, hey, that difference of 4, that's significant, right? We're able to say there's a significant post hoc test there. We don't find it with the Scheffé test. And again, that's because Scheffé is so safe. That's why we don't find that difference. We've reduced our risk of making a type 1 error. But the question is now, because we've reduced that risk of making a type 1 error, is our risk of making a type 2 error increased? And the answer is, of course, yes. And that may be what's going on here. Thanks.